In this lecture, I'm going to be going over some more information about the metric tensor. So just to remind you, the metric tensor is written as Gij, and it has the properties that if I take the metric tensor that is contravariant, so the indices are raised, and then multiply that by the metric tensor where the indices are lowered, or covariant, then actually let's make this ik. Then we're going to perform a contraction or a multiplication of the terms with the I. So the I indices will multiply out, and you'll get the Kronecker delta with a raised J symbol and a lower K symbol. So the metric tensor has the property of raising an index and lowering an index. So if we take a vector, so V with a raised index, so this is a contravariant vector, and then we multiply the metric tensor with the lower indices, then that has the property of producing a covariant vector where that index I is now lowered. So this lowers the index. If we take the metric tensor that's now with raised indices and we multiply it by a vector that's covariant, then what we should get is, actually I'll make this J, and then what we should get is V with a raised index I. Okay, so this one now raises the index. Okay, so let's take a little bit, let's take a look at some more with the metric tensor. So let's say I start with an orthogonal coordinates. So if we have that, then what we can find, and I'll prove this in a minute, is that the metric tensor I can write, so let's say I write Gij, that's covariant, that I can write as the elements are going to be equal to 0, or they're going to be equal to the scale factors that we used to make the basis vectors. And this is going to be true, it's 0 if I is not equal to j, or it's the scale factor if I is equal to j. So that's for the lower indices on the metric tensor. If I now have the raised indices, the contravariant, then what you would find is that, again, if I is not equal to j, then the component is 0. But if I is equal to j, then you get 1 over the scale factor. So if you can remember that the contravariant vectors were basis independent, which really physically meant that to turn that into a physical component, you have to divide out the scale factor. If it's covariant vector, then you have to multiply by the scale factor to get it in terms of a physical component. Okay. So if I look at this, that means that I now have this G, Ij, let's say, which I can write as a matrix where that's H1, 0, 0, 0, H2, 0, 0, 0, H3. If I take the determinant of this, I'm going to call that just G without any indices. And since it's a diagonal matrix, then the determinant is going to be H1 squared H 2 squared and h 3 squared. Okay, so I made a mistake somewhere earlier, and that is that this should be hi squared, and this should be 1 over hi squared. So like I said, in a minute we're going to go through and try and prove that. But anyway, so what you get is the determinant of the metric tensor gives you all these scale factors squared, the product of the scale factors squared. So if I take the square root of g, then I get just the product of the scale factors. And that, if you remember, kind of shows up in the definitions of things like the divergence or the Laplacian. So now I can write in very general terms that the covariant components of the gradient of some scalar function u I can write as just the derivatives of u with respect to this component, and where you then sum them up. For the divergence of a vector function, I could write this very compactly as 1 over the square root of the determinant of the metric tensor, the covariant derivative of the square root of the metric tensor times the contravariant vector components. For Laplacian, I can write this as, so del squared and u, the scalar function, as 1 over the square root of g, the derivative x sub I, square root of g, the metric tensor, the contravariant form, and then the covariant form of basically the gradient. So now we have it in we don't have to worry about we don't have to write it out in terms of all these h's. It's a very simple form where if all you need to do is take the metric tensor and plug it in, and everything is very simple. Now again, this is just for an orthogonal coordinate system, and so maybe if we go through the proof of this, that this is really true. So if I start with some vector, say a position vector, then I could write this in Cartesian coordinates as I dx plus j dy plus k dz. And if I want to write this now in terms of another coordinate system, then I could write this as I, the transformation, basically the partial derivative of x with respect to x sub n. So that's a different one. So Cartesian to some other coordinate system, dxn plus j dx dn, I'm sorry, dy, and then that's multiplied by dxn plus k dz dxn dxn. Or now I can write this as the basis vectors, a1 dxn plus a2 dxn plus a3 dxn, or just simply a sub n dxn, where now I'm using our old index notation where repeated indices, no matter where they are in imply a dot product. But these a's are the basis vectors. So a1 is equal to I dx dxn, a2 is j dy dxn, a3 is k dz dxn, where this is the case of the Cartesian coordinates writing those out. And so, okay, so we said before, or earlier in the class, I should say, that the metric tensor, Gij, was the product of these two basis vectors. So the basis vector I, the basis vector in j, or written another way, we could have written this position vector, ds, as the unit vector times the scale factor, dx1, where now we can relate the basis vector as the unit vector times the scale factor. So if this, in this definition of the basis vector as a unit vector times the scale factor, if we apply that to the metric tensor, then we would have a sub I dotted with a sub j, which would be the unit vector I, hi, dotted with the unit vector with the j index, times the scale factor with the j index. And so now these unit vectors are basically only going to be one if you're dotting together unit vectors that are basically parallel to each other. If they're orthogonal and I is not equal to j, then I would get a 0. You can't take the dot product of two orthogonal coordinates. So I is not equal to j. Therefore, what I have is Gij is hi squared. If I is equal to j, and it's going to be 0 if I is not equal to j, which was the covariant form that we had, I stated before. Okay, so that means we would have things like G11 is h1 squared, G22 is h2 squared, G33 is h3 squared, and then when I is not equal to j, that's 0. So forth and so on. So what we're left with is Gij is equal to h1 squared, 0, 0, 0, h2 squared, 0, 0, 0, h3 squared, which is what I stated earlier. Now this is the covariant form. If we wanted to find the contravariant form, then we would basically have to raise up those I and j indices, and the effect would be that I would now have each of those diagonal elements would be 1 over the scale factor squared. And so that's where we get this statement that if you want to make a covariant component of a vector into a physical component of the vector, you'd have to multiply by these scale factors. If you wanted to make a contravariant vector component into a physical vector component, then you would have to multiply by 1 over the scale factor squared. And so that's why we would have something very similar to, like in, say, cylindrical coordinates, ds is equal to dr plus d theta plus dz for contravariant. And for covariant, I would get dr plus r squared d theta dz.